the unified assertion-based framework for classical quantum program verification. All right, take it away.
Okay, thank you. I'm Yingte from PLanQC' Institute, and this is actually a proposal for my new idea of how to implement a tool for classical quantum program verification, and it would be easier to follow. So background, we have quantum algorithm, and we encode it into programs, and then it is compiled into circuits, and circuits are mapped to device and executed. So when we talk about verification, we talk about the second part here, because after this part, all the procedures are automated, and the encoding part and the proof for algorithm can be error-prone. So here, the verification is actually symbolic, and our goal, when I consider this work, is to push the frontier of symbolic verification on real-world examples. Actually, this starts from a story about a failure. This year, we also had a submission for POPO. It was about classical quantum relational Hoare logic, a very complicated concept. And I was in charge of the implementation part with almost the same goal as above, to actually build a tool that can implement, that can encode real-world cases. And the tool was in trouble with many reasons. One reason is the logic is complete, but the rules are too abstract, and they don't provide constructive transformation. They cannot be implemented. Another reason is the tool cannot be used intuitively. The predicate language we are using is really hard to encode and hard to parse. And also the way we implemented it. So we choose to do it in OCaml, thinking it would provide us more control over the tool, which, however, turned out to be technical debt. So in the end, I'm not sure how reliable the tool is. And we had to hack the tool to encode specific particular examples. So the tool was doomed, I thought, and then the result turned out as expected. But sometimes failure teaches more than success. And all the reasons, after I have been thinking about it, it can be concluded as one. So research papers ask for novelty, but building a good tool asks for something different. So what do we really want if we consider from the user's perspective, from the tool? I think we need a general, elegant design and intuitive, cognitive, aligned, usable tool implementation. That's the goal. It's not about something novel. But to achieve this, we need to make multiple design choices correctly. So there are several challenges. One challenge is the classical quantum methodology. What is it about? We want to introduce classical variables into quantum programs because many algorithms involve classical variable and their computation. And also, if you know that some variable are classical, you can represent and reason about them efficiently. But the problem is, how do you represent the classical quantum program state? So the method we have been using is directly taken from this paper, the first paper on the topic. It uses mappings as states. What does it mean? So here is a simple demonstration. You have two sets of variables. One set, for example, x here is classical, and the other set, for example, q here, it is quantum, and they're separated. And for example, here q is in superposition. After measurement, you get this state. So here, actually, the classical state and quantum state are correlated. And mapping means we use the mappings from classical program states to the quantum program states to represent the classical quantum program states. So this is the idea. It works. It works in theory. But if we implement it in implementation, there are some problems, like what is the context, what is the syntax for the mapping? And also the extra wrapping of mapping will make the reasoning very complicated. Also, if you use mapping for states, then when we talk about logic, when we talk about predicates, you also have to use mappings. And this is where the nightmare happens. So you really can't encode the intuitive idea, the description of states into that kind of predicates. So after some thinking, I think the problem can be solved by subtyping a different perspective to view this problem. One principle, all variables are fundamentally quantum, even if you consider classical variables. And they can be identified by types. So what do I mean by classical? Here, some setting for the program language, but essentially, when you have a register which consists of a set of variables, and the state satisfies the property that after measurement on this register, the quantity stays the same, then we can say that the register is classical. So here actually, classicality becomes a property to be satisfied. It is not something that is separated from quantum. So that's the idea. And by identifying these special registers, we can make use of the classicality and simplify the reasoning about the classical part as well. Yes, the classical part can be identified by context and typing. The context should be, of course, declared when you define the program. And another important theoretical result as a conclusion is that this method is isomorphic to the mapping method, meaning that this way of representation and symbolic reasoning has arguably the same complexity. And this is about states. And if we move on to consider predicates, things are more chaotic. So there are different ways to describe the property of quantum states. One way is use subspaces, and we decide whether one quantum state satisfies the subspace or not. This is called the qualitative way, and the other way is the quantitative way, where we use observables and we talk about the expectation of quantum states on the observables. But they all have their drawbacks. For example, the subspace way cannot describe properties, and the observable way, the quantitative way, cannot express logic connectives. So, okay. So in short, if we start from our intuition, we want to write something like this. So we have classical part and quantum part. We can combine the predicate on this. And this we can design a language for this. This is similar to Boolean algebra. But the difference is that we have a special terminal term here represents the subspace, actually the one-dimensional subspace. And the semantics is also different. They are not interpreted into Boolean algebra or Boolean lattice. They are interpreted into subspaces. So we are still using the subspace style predicate. And they are described by also modular lattice. So here is the trick. Also modular lattice is a generalization of Boolean lattice, and the only difference is that they do not obey distributivity. So subtype comes again. Boolean lattice is a subtype of also modular lattice. And about decidability, also modular lattice is it's a still open problem about it, and we want to use existing tools like SMT solver to solve the classical part because they will be blended together. And in short, this can be decided by typing. So you can identify which part recovers the property of Boolean lattice, and you can utilize this fact to do proof nicely. And here is an example from our real work. So x and y are classical variables, and here R is a quantum register. These two predicates are identical. They are reasonable, but how to prove it? The trick is that we can identify the parts x equal to y as commuting to the two subterms of disjunction. And this means the distributivity recovers, which is not always the case for osmotic lattice. And then we can put the x equal to y into the two subterms. And then the classical reasoning will tell you that you can replace one with the other. So this is an example how subtyping can help you build a predicate language that fits your intuition and can be proved easily. So this is about predicates. And the next part is assertion, language, or logic, implementation, and automation. So they are really like a problem that involve these entangled parts. What is the best environment to do program verification? I would say for quantum it is definitely interactive stream prover. The reason is that for classical program verification we have the SMT solver, so it can prove the relation between predicates automatically. But for quantum, the proof involves a lot of mathematical parts. But the problem, or the opinion I have is in interactive stream prover or logic, actually it should be considered as a proof technique instead of something that you must rely on. So different from like implementing a program verifier in C++ or OCaml, where you must rely on Hoare logic. Otherwise, if you cannot encode your property in the logic, then you cannot deal with it, you cannot prove it. It's not the case for interactive stream prover because the logic foundation has changed from Hoare logic to the type theory. And actually you have Hoare logic and the semantics of the language formalized in interactive stream prover. So think about it in this way. Even if you have a very complicated, very special property of correctness that cannot be encoded using Hoare logic, you can still encode it using semantics and try to prove it. Although the proof would be tedious, obviously, but automation will counter this problem. And we all know that artificial intelligence has been proved to be really good at it. So the thing I want to say is that when we do it in interactive stream provers, the first priority is not to build a complete Hoare logic. The first priority is to design a general language that can express your correctness property nicely. And what do I mean by generally and nicely? Here, this is my idea, and actually it follows the research result from Gilbert and Robert Rand for probabilistic programs. So basically, we have multi-level assertions. Here, P here is the subspace predicate we have been talking about, and E is the value expressions, meaning that intuitively, when we express the property, we talk about expectations and arithmetic operations on these expectations. And the real predicate, the real assertion we talk about is we compare the expectations in different ways and compose the comparisons. So also this is general because it allows you to talk more. It allows you to describe your intention better, and also it aligns with intuition. So then with this kind of assertion, we can like compare different ways to design the Hoare logic. This is the classical one. Notice that here the implication is a classical one. And for the Hoare logic, the quantum Hoare logic we have been using, it is actually not implication. It is the comparison between the expectations. So here, I want to make a point that in this quantum Hoare logic, we are actually hard-coding the special kind of correctness property we want to prove, that is comparing the expectations. We hard-code it into this kind of quantum Hoare logic. And if it does not follow this pattern, then we cannot prove it. For example, when you want to consider concurrent programs, or when you want to prove by separation logic, you want to have like the conjunction, disjunction between the predicates. It's not possible here. But with the multi-leveled assertion-based Hoare logic, we can do it. And actually, in form, it recovers the simplicity of classical deterministic Hoare logic. And one fact is, actually 2 can be embedded in 3. So, to conclude, you may ask, what does the final product look like? I imagine it should be a lean project, formalizing the language with assertion language, semantics defined, and Hoare logic is a proof technique. And also automation, I haven't mentioned it, but it's really important to make a usable tool. We should have automation, and it should demonstrate through real-world examples. For example, take show algorithm and encode it using the programming language and prove the correctness. And also a natural, like future work, work in the future is we can consider compiling the programming language into target circuits. So key takeaways: use subtyping for classicality. And we should unify classical quantum predicate by osmodular lattice. And for assertion language, use subtypes with multi-level assertions. And for verification in interacting provers, so the first priority is a general and expressive language. So that's my opinion and the blueprint for the implementation in my mind. And I'm happy to hear your suggestions and comments. Thank you.
Thank you. Questions? Okay, I'll start off. So your recommendation there seems pretty similar to CoqQ, I think, because CoqQ is, it's a verification framework in the Rock Proof Assistant, but I believe that most of the actual proofs they went through a Hoare-style logic. So can you talk a little bit about the similarities and differences there?
Thank you for the talk. I was just wondering about the classical world clashing with the quantum world. At the bottom of it, sometimes it seems that it's like the disjunction as an idempotent operator clashing with the world of linear algebra, where you have plus, which is non-idempotent, but you can. So in other words, Boolean rings versus Boolean algebras, or saying instead of having disjunction, but having XOR as a primitive. Because then you could say like, oh, what's a predicate? I was just thinking, what's a predicate that's not 0, 1, maybe just mapping into a base field, K, it's like, and then it's an element of the dual vector space, so a predicate would be in this fashion embedded into the spaces of quantum-like computing. Do you see these things in practice popping up? Is like having disjunction being a nasty thing to deal with as a primitive?
So you're asking whether we really need this disjunction.
Well, you can code it, right? But having as a primitive XOR basically, and then just saying, oh, disjunction is very complicated. You have to just code it in terms of XOR and one minus and so on.
So
right?
you mean that in classical logic there is a famous result that you can use XOR to encode everything? Maybe
it's more like the difference between Boolean rings and Boolean algebras, because the Boolean rings you have an additive inverse, right?
Well, okay, that holds for logic, but I think we can consider the problem in different perspectives. So as Leo, the developer for Lin said, you have to work on the correct level of abstraction. So here I'm talking from the lattice level, because in the lattice you have the joint, the joint meet, and they are defined by the conjunction and disjunction. So there is a very close connection between lattice, the algebra representation, and the logic part. So that's why we don't consider it all here. So it's natural to use this in algebra. That's why. Yes.
Lattice algebra, right?
Yes.
Yeah.
Yes.
Okay. Thank our speaker again.
Yeah.